So in lesson 9.1, we looked at the idea of a transformation, just any change in size or shape or position of a line, a polygon, a point, anything like that. What we're going to look at today, we looked specifically at the transformation that we called translation. And we said that a translation, you can kind of call it a slide. It's where every single point that makes up a shape moves in the same direction, the same distance. So we're going to use GeoGebra today to give us a little help here and to review what a translation is, or a slide. So here we have a triangle made of 3 points, and we can see our points here. A is at 0, 0, B is at 1, 2, and C is at 2, 0. Now a slide would be any change where they all change the same. So if we wanted to say slide to the right, like they do in some of those popular dance songs there, if we slide to the right, that means the x-axis is right and left. So if we want to go to the right, that's positive in the x-axis. And so we're going to add 1 to each of these x-coordinates. And if we watch what happens to our shape here, I'm going to change this. So I'm going to change, watch as I change these x values. So we're just going to add 1. So 0 plus 1 is 1. And that moved this point, A, from here to here. Moved it over 1 unit. But I want to do that to all of my points, right? A true translation, all of the points move over. So now my B moved over, and I'll move my C over by 1. And notice I still have the same shape, right? I still have the same shape, it's just now everything is shifted over 1 unit. And we're not just hindered by looking at just the x-axis. We can change both x and y and have it slide, diagonally. So if I added 1 to x and 2 to y, that would be taking this entire triangle and moving the whole thing over 1 unit and up 2. So if I go plus 1 in the x, plus 2 in the y, and again I have to do this to all of them, so plus 1 in the x, plus 2 in the y, plus 1 in the x, plus 2 in the y. And again, notice I still have my same shape here. I've just shifted it over 1 and up 2 units, the whole thing. So this is the example of a translation. We're just taking that same shape, sliding it from one point to another, or from one area to another, and we're just changing its position. Notice the size is the same and the shape is the same that we started with. This is an example of an isometry, right? Just sliding it around, the figure itself stays the same size. So this triangle would be congruent to the original triangle that we had starting at the origin, so it would be an isometry. Now, what we're going to learn about today is what we call a reflection. And very often, when you see reflections in the axes, so reflecting across the x-axis or reflecting across the y-axis. It doesn't necessarily have to be that way, but very often that's what we end up seeing. And a reflection is really just that. If you were to think about, let's say you were standing at point A, and you were looking into a mirror that was along the x-axis, right? If you looked at the mirror and saw yourself, you would see yourself as being 2 units away from the mirror. Well, you are 2 units away from the mirror, but actually when you see your reflection, you would appear to be 4 units away, because you're standing 2 units away and the reflected image of you would be 2 units on the other side of the mirror. So what we see when we have a reflection is actually a changing of the values to represent a movement across a certain axis. So in this case, if we were reflecting across the x-axis, we would take this point and we would reflect it down here, right? So our new point would be at -2, 2, -2. Would come straight down here. So we can do that. And if we're reflecting in the x-axis, notice our x value is still going to stay the same, but our y value changes. So we go from +2 down to -2. So we can just change the sign there and put a negative. And we can do the same here. B, again, if we reflect B all the way across down to here, the x value is still going to stay the same, but the y value goes from positive to negative. So we can change this y value from positive to negative, and the same for c. And notice what's happened. We have our same shape that we had up here. The size is the same, the shape is the same, but the position has changed. It was pointing upwards, and it was in this quadrant a minute ago, and now after our reflection, we've reflected down here to the bottom. We can do the same thing in the y-axis, right? Think about what happens if I were to reflect in the y-axis. My y value, for example, if I were to take A, my y value would stay 2. So the y value stays the same, but I go from a positive 2x value to a negative 2. So a reflection in the x-axis changes the sign of the y value. A reflection in the y-axis changes the sign of the x value. So we can reflect this over here, and we can change the signs in here. So we can make that x negative, and we can make this x negative, and we can make this x negative. Now notice again, I have my same size, same shape, so this is another isometry. But notice something, this may look exactly the same as the triangle that was over here. But if we think about the triangle that was over here, A was in here at 2, negative 2, and C was out at 4, negative 2. So A was on the left and C was on the right. Here, A is on the right and C is on the left. So notice they've switched positions. So this is essentially what a reflection is. Now your textbook, we're going to get to that in a second. The textbook gives sort of the craziest, weirdest definition of reflection that I've ever seen, but we'll talk about it and try to deal with that a little. It's just sort of a strange way to go about it. But again, keep in mind, you do not have to reflect across the x-axis or across the y-axis. You could, for example, plug in a value here of y equals x. So we've got this line y equals x, and we could reflect across this line y equals x as well. So C would reflect over to here, B would reflect over to here, and A would stay right where it is because it's already on the line of reflection, if we can visualize that. So I'm not going to go through transforming all of these points in here, but we'll see more of that in the examples in the workbook. So let's jump on over to the workbook and see if we can't put a little definition to this. Okay, as I mentioned, in the workbook, they give kind of a crazy definition, and I know it's going to confuse some people, but let's work through it and see exactly what they're talking about here. It says a reflection in line R is a transformation such that if a point A is on line R, then the image of A is itself, right? So here's point A, and if you're reflecting in line R, point A is point A, right? The image and the pre-image are exactly the same if the point lies on the line of reflection. Then it says if a point B is not on line R, so here we've got B out here, then its image, B prime, is the point such that R is the perpendicular bisector of B and B prime, so of the pre-image and the image. So what they're saying here, so here's our image, here's our pre-image, and here's the line of reflection. Essentially, if we have a point that's not on the line of reflection, the image and the pre-image are going to be the same distance away from the line of reflection, and the line between the two of them will be at a right angle. Which makes sense if we think about what we had done. And if we think about our x and y axis, and we had, a point here. When we were reflecting in the x-axis, we started here and we came straight down, right? A vertical line meets the x-axis at a 90-degree angle, so there it's perpendicular, and the distance was the same, which made the x-axis, which is the line of reflection, the perpendicular bisector. If we think about when we reflected in the y-axis, right, we can just take this up here And now we're going, again, perpendicular. A horizontal line is perpendicular to the y-axis, and we've got the same distance, so the line of reflection, which is the y-axis, is the perpendicular bisector between the point here and the point here. So it's just reflecting across the line. But again, it doesn't have to be the x or y axis. It can be any sort of axis, any sort of line that we can draw. You can reflect across. Okay, so let's see some examples and see if that helps make sense of some things. We look here, they want us to find the reflection images. So it says if point Q, which is at -1, 2, and we can see it here, it says point Q is reflected across the line x equals 1. So if the line is x equals 1, that means it's a vertical line, right? Every point in there has an x value of 1. So x equals 1 would be a vertical line crossing through 1 on the x-axis. They want to know the coordinates of its reflection. Well, again, if we start here at Q, we can see that Q is 1, 2 units away from that line x equals 1. So if it's 1, 2 units to the left, when we're done it should be 1, 2 units to the right. So I don't like the fact that they... Let's make a different line here and see if we can't make it a little easier to see. I'm going to change the color of this line. Okay. Hopefully that will make it a little easier to see. So the red line is x equals 1. The black line here, the vertical line, is the y-axis. So we can see that right now we're at -1, 2. And if we're going 2 units to get to the line of reflection, we need to go 2 units on the other side of it when we reflect. So our new point will be 2 units to the right. So right about there. And we can see based on our x and y axis that that's at 1, 2, 3, +2. Let's go ahead and check here. It says Q is 2 units to the left of the reflection line. So its image is going to be 2 units to the right. Therefore, we get 3, 2. All right, as always, quick checks are for you to do at home on your own. And we'll move on. We've got 2 more examples and then we're finished. It's a pretty short lesson. Here they say drawing reflection images if you start with a triangle XYZ and they give you vertices. So this is probably one that you're going to want to throw some axes up here. You can put a little x and y axis up here. So they give you some values here. They say x is at 0, 3, so we can put that about there. 0, 3. And y is at 2, 0. So 2, 0. And z is at 4, 2. So say 4, 2. About there. Again, I'm just kind of eyeballing these. And they want us to draw triangle XYZ. So we've got that. We can fill in some lines here for XYZ. Connect those. All right, so there's XYZ. And they want its reflection image in the line x equals 4. So let's take this whole thing. Let's maybe move it. Select all these and move them together. Move it down here. So we've got all of these, and they want the reflection in the line x equals 4, which is going to be out here. Right? We said this point here was actually at 4. So there's the line x equals 4. We'll go ahead and make that one red again so that you can see it. So we're reflecting in this line. Well, that means that this z is actually not going to go anywhere, right? Z is going to stay put. But down here, this one was y. Y is, if this is at 2 and this is at 4, it's 2 units to the left. So the new value, use green, the new value is going to be 2 units to the right. 2 units to the left. Now it's going to be 2 units to the right. And then here, this one, if this is 4 units to the left, right, because its x value is 0, then the new point needs to be 4 units to the right. And again, just kind of eyeballing, and we get our new image. So we can see how the red one has flipped around and reflected in this red line. So if we do that, they ask us to locate the points, and we can now figure those out. If this was at 0 and this is at 4, then this is going to be 4 more to the right. So all of those points are going to be 4 more to the right. So this would be this point here. The new image for x would be at 8,3. Z we said would say stay put, so that's still going to be at 4,2. And y was at 2. This is at 4, so this is going to be now 6,0. Okay. One more example, and then turn you loose on the quick checks. Here they're telling us that D is the reflection of, D prime is the reflection of D across line L. So here's D, here's the image, and here's the line of reflection. To show that PD, right, so PD would be this segment, and PW, this segment, form congruent angles with line L. So they're looking at this angle in here, and this angle in here. Okay? So when we look at the reflection, we know that if these are reflections, we can draw a line right in here. Between D and D prime, and that should be 90-degree angle in there, right? We also should know that this segment and this segment are going to be congruent as well to each other. So that might help us get a little further in this. So the way they do, they say because a reflection is an isometry, we know that PD and PD prime are going to form congruent angles with the line. So if we looked at triangle PD and then this point here, we know that that's going to be the same as triangle PD prime and whatever this point is here. So these angles are going to be the same, these angles are going to be the same, this segment, this segment, this angle in here, this angle in here, and so on. PD and PW also form congruent angles because they're vertical, right? Or PD prime and PW. So we're looking at this angle here and this angle here, are vertical angles. All right, so then when we continue on, the transitive property tells us, well, if this angle and this angle are the same, and this angle and this angle are the same, then we know that these two angles will be the same as well. So PD and PW are going to form congruent angles. So hopefully that makes sense. If not, again, we've got all the class time to work on this and to clear up this idea of reflection. But give it a shot, give the quick checks a shot, and we will continue to work with reflections, and we'll learn some more transformations as we continue.